Okay. Hello, everybody. Wait for everyone to comment. Okay, so my name is Tommy. I'm from the Netherlands. I'm doing a PhD in Eindhoven, in the south of the Netherlands. I've been here in San Francisco for almost a year now, and I've been working on an internship at Amazon Frontier AI and Robotics. And today I have the chance to present our work. Our work is selected as a highlight paper at CVPR, so I will also present it in 2 weeks in Denver. Our work is on world modeling and doing that efficiently. And it's a joint work with people from Amazon and also from my university and from the Johns Hopkins University. So I want to start with a way that I think about AI, and I want to start with the data pyramid. So recently we've seen a lot of big breakthroughs in virtual AI, in language modeling, and also already a little bit in learning from experience. But I would say most breakthroughs so far have happened kind of here. So learning from language, and then learning a little bit from experience with whatever comes out of that. Now I want to make the point that there is much more data available to learn from in this world, and we haven't really scratched the surface yet. So language is written by humans on a computer and put on the internet somewhere after the 90s. And at the same time, video and images are recorded by cameras. And a camera doesn't require a human anything to do except turning it on and putting it somewhere. A camera can stay somewhere for years and record video kind of for free, no human effort involved there. And because of that, we have much more visual data in this world than that we have language data. So I think it's very important that we put a lot more focus on this visual data, because learning from language brings us to a very smart digital intelligence, virtual intelligence. But in order to get very good physical intelligence for robotics, I argue we need a lot of more visual understanding. So I would say that the most data we can collect is actually images. Because images are very easy to collect. And after images, it's video. And in this presentation, I'm going to focus on video specifically, and we're going to leverage some good image prior. And when you learn from video, I think the most natural way is to actually predict the future. So similar to language modeling, predicting the next word in video, we can predict some frame into the future. And we can also model a world model. So why would we want to do that? I would say for an agent to operate in this world, they'll have to be able to imagine the outcome of their actions. So they have to be able to imagine the future. And in order to be able to imagine the future, you need to be able to predict different possible outcomes. In this presentation, I will not consider action conditioning or language conditioning, but I will just focus on modeling the world and thus modeling the most broad distribution of possible futures. And in fact, actually, the future is so multimodal, it's infinite. There are infinite possible branches from this point onwards. So it's quite an interesting problem. And a practical example is for a self-driving car. If it's waiting at a crossroad, then a pedestrian may cross or it may wait, and these are both valid futures, and I would argue both need to be considered. And then we have some simple world models. I term them here discriminative world models that basically collapse the future into one prediction. And what tends to happen there, if you do that naively, is that this prediction regresses to the mean. So you'll get a blur of the pedestrian staying and walking at the same time, which is obviously not realistic. And generative models, on the other hand, they can sample diverse futures. So generative models, they learn a distribution of possible futures, and at inference time we get sample from this distribution to get a sharp future. One issue, however, with these generative models is that they are quite slow and expensive, because these models not only learn the multimodality of useful things, but also the multimodality of completely useless things for robots, such as, for example, the leaves in a tree. And I'll get back to that later. Now, for illustration, so you guys know what I'm talking about, here's some sneak peek of some output of our model. So you have an idea of what we're working with here. And this is a simple video of a guy walking in New York, I think. And these are like the context frames. And this is what happens after. And as you can see, the camera is kind of moving. And this person also is moving. Maybe it's going to stop, maybe it's going to accelerate. We don't really know. So the future here has different possibilities. And our model predicts these 4 different samples of possible future continuations. And then this turns out to be what the real future is. And these are segmentation maps, by the way. So the purple color means there's a human there, and the blue color means there's the sky, etc. So our claim is that world models are heavy, but they don't have to be so heavy. So I would say there are 3 main reasons why these models remain so slow. The first reason is that pixel fidelity generation wastes capacity on being photorealistic. And I'll get back to that. Second reason is that sampling a single future from this model requires multiple forward passes of the model. Obviously also slower than doing a single forward pass. And then thirdly, every frame is re-encoded into a lot of largely redundant tokens. And then already a spoiler for our final model, which is much smaller, there's only 1 forward, and has only 1 token per future. And I'm going to explain how that works. So first of all, why does pixel fidelity generation waste capacity on photorealism? Well, these existing generative world models usually work in a latent space that was trained to reconstruct pixels, so that for us humans, it looks nice and realistic, right? But if we train a world model to predict these photorealistic latents, the world model needs to allocate its capacity, its parameters, its compute on having good textures, good lighting, fine details. And a lot of these things are not important for a robot. So most of that signal is irrelevant for downstream decisions, such as a car going left or right. Doesn't matter how the leaves are blowing. I'm kind of repeating Jan LeCun here with this example, so I'll give him the credit. But I think it's very illustrative for the problem here. And therefore prior work has focused on predicting semantics rather than pixels. So if we start with learning from images, there are self-supervised learning methods such as Dino V3. This method takes images and nothing else and learns just from those images dense semantic representations. And here on the right, I show a few example images. And on next to it, I'm showing the principal component analysis visualization of those features. And you'll see that different objects have different colors, and the same type of objects have a similar color. And from that we can infer that the model mostly is storing the semantic class of these objects rather than their specific appearance or the fine details in these objects. And the paper Dino World basically took this model and said, can we use this image encoder instead of these latents optimized for pixel reconstruction? Because this model should have already kind of discarded these irrelevant details and focus on the important part. So they show that if you train a world model on these Dino features rather than these pixel-based latents, you can make the task so much easier and have a much smaller model be as accurate in forecasting the future as a big pixel-based model. And how do we measure that? Well, instead of measuring the pixel similarity or the distribution of images from a pixel perspective with a metric like FID or PSNR, we shift to measuring something that is more interesting. So the semantic accuracy. So for example, the segmentation MIOU, which says something about how good are the segmentation masks. Or the depth RMSE. So this is a measure of how good do the predicted future features estimate the depth with respect to the real future. By the way, if there are any questions, please interrupt me during the presentation. So you'd think, okay, we get rid of all these details, then these latents should be, or these features should be much smaller. But that's actually not the case. So if we naively encode each frame with this Dino Vision encoder, and then make a cube, repeat these features for every frame, we get a very big spatial temporal feature cube, which is from the, the VIT base size onwards, is more information than the original pixels. So these features do highlight what's important, but they take up a lot of information, a lot of data. So our question here is, can we store this in a more efficient manner? So we've highlighted the semantics, but we haven't yet stored it in an efficient way. And the hypothesis here is that semantic features, they should require much fewer dimensions than something that needs to reconstruct the original pixels, right? They've just not been compressed yet. And then taking this one step further, since we're looking at video here, the change between the semantics, between the previous frame and the next frame, is actually very simple, right? It's some kind of encoding of this car moved a little bit forward, and for the rest, maybe the camera shifted a little bit. And we don't have to store the whole frame from scratch again, right? In other words, if the frames are close to each other, if the frame rate is high enough, the change between the frames is relatively low dimensional to store. So is there a way to compress this semantic change into just one token per frame? So you could ask, why one token? Well, I would say, if one token is not enough, just increase your frame rate, right? If there's a lot of motion, just have a higher frame rate, and now there's less change between each frame. So instead of changing the number of tokens per frame, we should rather change the frame rate. Okay, so how? Now it becomes a bit technical. So let's say we have two frames from a video, and it's pretty small, but there's a car driving into the camera, and we get these Dino features. So this is VFM, stands for Vision Foundation Model. So we get these spatial features for both frames, and we train an autoencoder to reconstruct those features. And the autoencoder has a very small bottleneck, that is this single delta token. And with that single delta token, we must be able to reconstruct the next frame. Now specifically, we have an encoder, that's the compressor, and the encoder takes in the features of both frames, and it outputs just one token. That token should contain the difference between those two frames in an abstract manner. And we train it as such, because we feed this delta token to a decoder, and the decoder must be able to reconstruct the next frame using the previous frame and that delta token. And if we train it as such, a representation emerges that captures the change, rather the semantic change between these frames. So now we want to train a world model, right? We've captured only the semantics, only the things we care about, and we've compressed it to a very compact space. So now we should be able to make a much more efficient world model. So how do we do that? How do we do next delta token prediction? if you may recall, there are many possible futures, so there are also many possible delta tokens. So the idea is that the predictor, the world model, should be able to map different inputs to different outputs. And the input distribution can be a simple normal distribution, and there are infinite possible noise factors. And just like in a diffusion model, we want to map every noise factor to one sample. And instead of making an iterative denoising process, we do something more simple here to make things easy. Because since one delta token is very small, we can, at training time, sample different futures and basically look at which future corresponds the most to our ground truth sample and only supervise that one. So if we have a ground truth video of the car moving into the frame, and well, this is pretty logical, it comes closer to us, then most likely one of its predictions will predict that, right? But maybe another noise input would predict that the car actually turns left. Let's say our ground truth video does contain this more rare example where it goes left. Well, we sample a bunch of futures and we find the future that represents the car going left. And then we say, okay, for this input, the predictor meant to say the car goes left, so let's improve that prediction. Now, this works even if you like randomly initialize the model. It starts to learn to map different noise inputs to different futures in a single forward pass. So we call this resulting model Delta World, and basically Delta World efficiently predicts many different futures in a single forward pass. So we can easily in parallel predict a bunch of futures. We do it during training, and we can do it during inference time. And we can also do it now in a single forward pass. And these delta tokens that we predict, if you need the spatial features for downstream tasks, you use the tokenizer decoder to go from the delta token to the spatial features to then do depth estimation or segmentation or whatever. So this is the only slide with results. So basically, our model performs on par or a bit better than an existing pixel reconstruction-based world model called Cosmos with much less compute. And specifically, this is on short and midterm forecasting. So that means a little bit into the future. That is like 200 milliseconds to 600 milliseconds into the future. What I'm showing here is 600 milliseconds into the future. I'm showing the best prediction out of 20 and the mean prediction out of 20 for our model and for this prior model. And this model works on pixels, so if we want to measure semantic segmentation, which we do here, we first have to turn these pixels into dino features, and only then we can also do segmentation, and that's how we do this comparison. But the takeaway here is that we can do with more than 35 times less parameters, and we can do with 2,000 times less floating point operations. And compared to previous models that use dino features, we have about 1,000 to 2,000 times less tokens. So the conclusion here is that video is an abundant data source, but I'd argue that its high dimensionality and its noisiness makes it quite inefficient to learn from. And to make things easier, we can effectively reduce this dimensionality actually by multiple orders of magnitude. And we can then train a world model that focuses only on the change, the semantic change between the frames. And that boosts both the speed and the accuracy. And I think this offers a compact representation to do visual understanding, but also visual generation at scale, making it much more scalable. So yeah, what's next? There are a couple of points that can be improved. And first of all, I would say that the distributional modeling objective, where we sample a lot of futures during training time and supervise the best one, is inherently limited by how much we can sample during training time. And even we can sample a lot, we won't estimate the true distribution like a diffusion model would, for example. So I think that's one interesting direction to improve upon. Another important direction for visual generation specifically is error accumulation. So when you only predict the change between frames, if you make any tiny mistake, it's going to add up. And if you re-encode every frame from scratch, you can more easily recover from such mistakes. So this is a challenge specific to predicting deltas. And I think there are definitely solutions to this problem, but that's a research project on its own, which I'm working on right now. And another thing is to learn these representations end to end. So we've shown a proof of concept here, but it's not very elegant if you have frozen modules and multiple modules in general, not very elegant. So I'd say we should be able to learn these representations end to end, but that also requires further research to make it more similar to a real joint embedding predictive architecture. And finally, I would say, like I just mentioned, we should be able to unify this all into one native multimodal model. But I don't think this representation stops us from doing that. I think it's actually very suitable for it because now we just have a 1D sequence of tokens also for video. So the final goal here is to scale this to all videos we currently have and do this efficiently with these delta tokens. And that concludes the presentation. We have our code and weights online if you're interested in working on any of the previous remaining problems. And thank you for your attention.
Yeah, maybe my understanding is wrong. So by my understanding, your method is change the feature from the pixel to the semantic feature, and because you change the feature due to the latency, because the token is less than pixel. But this part I understanding. But I remember you say you also change the evaluation weight for the compared to the pixel.
Yes.
So can I ask how you can compare apple to apple comparison because two method because the evaluation weight is changed?
Yes, that's right. That's a good question, and that's also also, let's say, a down, how'd say, the pixel-based model is to a disadvantage there, right? Because it predicts pixels, and we need to re-encode the pixels with a dyno here to then be able to do semantic segmentation or depth estimation. We can also do the opposite, right? So we can try to turn our predicted features, semantic features, back to pixels, which won't look as nice because this model was not optimized for it. And then we can measure some of these pixel-based metrics like FID or PSNR, and then it will be much worse. So, I think it depends what you care about in the end. What do you want to use your world model for? If you want to use it for TikTok videos, then you probably want to look at the pixel-based metrics. If you want to use it for a robot that needs to interact in this world, then it doesn't matter that it doesn't look nice. For me, it should look ugly, but realistic in the sense of the motion and the location of objects and no hallucinations there.
Yeah, I mean, my question is that, so because we need an apple-to-apple comparison, and then we will say which method is better. It doesn't matter about the feature,
right.
Which one with the feature, which way with the evaluation, but it doesn't matter about the which kind of the method to perform this one. But my question is that, is it possible to have we use the same input, same output, and
so,
we have the same apple-to-apple comparison to see, the second, the delta token is performs better.
Right. Oh yeah, we definitely do that in the paper. So we compare to a dyno-based model that doesn't do the delta compression. Then we can do apple-to-apple comparison. But if we want to compare to an existing generative world model, then we cannot because it works in pixels. So either we penalize one or the other model. But in the paper we specifically have like a step table where we go from a discriminative dyno-based world model, and first we make it generative because it's not. And then we do delta compression, and then we look at does it get worse or better? And what happens is it remains as good on mean performance, but it can actually predict a better sample out of 20. Even though there might be reconstruction loss when you make your rollout longer at the short horizon, it does not degrade the performance in the apples to apples comparison.
Sir, thank you for explanation. I have one more questions about the latency. From the math, I'm understanding you because the benefits are just sequential token. It saves a lot of time compared to the pixel because it's 3D is more token.
Mm-hmm.
But would you have the comparison how much you save the time for something to the latency or something?
Yeah, so I didn't do any time measurements because they take a lot of time. I'm not too sure. I've done time measurements later on, and I think it really depends how long the sequence is. So in this paper we kept it simple. We just had 8 frames, but there's no reason to keep it so short. And if you start training on more frames, there's, especially for training, there's a huge difference. Like I cannot train a spatial dyno world model on say 64 frames. It doesn't fit, not even in the best GPUs. And this one easily fits. So and then for inference, it's a bit less. You still get speed up, and then it really depends how long is your rollout. So if you roll out very long, you get more benefit from not having these redundant tokens. But you have all other issues like error accumulation.
Thank you.
Yes.
Yeah. I think the main benefit for this one frame, one token is compression, right? Like so that you have way higher efficiency. But in the conclusion is that it improves short-term and medium interval. I thought if you have a high compression, you should do a better prediction of the longer time frame. Did you guys do the test on the prediction for the longer term? I thought that would be the main benefit of the higher compression of the.
Well, yes, that's where, like I just said, that's where we would profit the most.
Yeah.
But then there's the issue of error accumulation there. So then we need to do a little bit more to make sure that the rollout remains stable, so that we don't accumulate error, and then yes, it should be much even more interesting there. Yes, absolutely.
But did you compare the delta versus dyno in terms of longer time interval?
No, in the paper we only do 1 frame, 3 frames, right? And then later on I've been also doing longer rollouts. And then, like I said, it's a bit challenging to train that, or can be depending on the resolution. But I can make it work there, but it's a bit more complicated. But that's really the next paper, basically. Yeah. I don't know who was first, but I think you were first, right?
Are there certain frame transitions that are too high of entropy to model in one delta compressed token, like fast egocentric motion or something like that?
Yeah. So the most extreme example is scene cut, for example, where that's just 2 completely random images. And what happens in this model is that it just then resorts to absolute compression. So it gives you a lossy reconstruction of the second frame, and it doesn't really look at the previous frame because it's irrelevant for it. And then you can kind of improve if you keep going with some smooth motion again, because then you have some more tokens to improve it again. Does it make sense?
Yeah, so training with longer rollouts might resolve that issue then, right?
Depending on how you do it, yes. Yeah. Yes.
Yeah, I have 2 questions. One is, I think, kind of follow up with the previous ones, which is, so when we say apple-to-apple comparison, I think one application is obviously robotics, as you said. So as a practitioner, I care about the backbone, right? So if I use this as a backbone versus a dyno,
Yeah.
Did you guys have any comparison in that? Because for me, that will be apple to apple, just to see some downstream task performing better with the better tokens.
Right. Yeah. So if the downstream task is predicting 1 or 3 frames into the future, then it performs better, or on par but faster. That's what we show in this paper. For other tasks, that would be interesting to see that. Yeah. I'd say why I don't know why it would not work for video understanding tasks, for example, like classification.
Let's say some like manipulation benchmark in sim, something like that, instead of using like ResNet or.
Yeah. Yeah, I think that's very interesting. I hope someone's going to do it. I don't see why it shouldn't work. It should be easier than visual generation, I would say. It's just a way to store your history. But I think there are different challenges if you're doing if you have like a VLA, then there are these challenges with having a history of frames, right? Rather than just having it like, what's it called, Monte Carlo, I think. But yeah, anyway.
Sorry, I have a second question.
Yeah, sure.
So you mentioned you don't have any conditioning on language or actions.
No.
So is it why you have to do this many sampling to find the closest? Because if you have the conditioning, you would just have the run through matching very easily, probably.
Well, it depends. If under the condition there's still multimodality, then you could still do the same thing. But does make things easier, obviously. But yeah, I guess it becomes easier to evaluate when you have some action conditioning or language conditioning.
Because in your car example, for example, yeah, indeed, car might be moving towards you, or maybe you're moving towards the car. So if you don't have the action conditions, is there just two possible?
Yes.
Likely?
So that's why, yeah, like prior work also does this, and we basically report both the mean and the best. And the best is like, yeah, we just look like which future matches the ground truth the most. You could call it cheating, but it's if you compare another model in the same way, then it's a fair comparison. If we had action conditioning, we could do it a bit differently, maybe. Yeah.
Yeah, thanks.
Yeah. Please.
Yeah, I'm curious, why did you choose to do this random sampling and then use the closest one to do the loss? It seems a little ad hoc. Why not just use diffusion, which seems like the more proper way to model these marginal distributions?
Yeah, good question. The deadline was coming up, and I didn't get diffusion to work yet. So then this worked, and we just wanted to get it out there as a proof of concept. And I can already spoil that diffusion also works. Yeah, and because there are so little tokens in the model anyway, doing a couple NFE is not such a big deal anyway. Though it remains interesting to get diffusion to work well in such latents. There are some challenges there, but yeah, there's no reason why not. Yeah.
Okay. And then I have one more question about, so I guess, so you're using dynamo features, right?
Yeah.
What, I guess you could have chosen like any embedding model, but like choosing any one of them kind of then restricts you in what it is good at predicting, right? I guess dynamo is good at predicting maybe segmentation mass, and then I guess you're reporting like performance on predicting segmentation mass. So
yes.
That's not super surprising that that's going to work well, but maybe, I guess now you can, let's say, I don't know, do pose estimation or something like that as well, maybe. So
yes.
yeah, I guess I'm not sure what the question is. I guess the question is like, yeah, like how did you choose the embedding model, and do you think it can be kind of like, I don't know.
I think we should learn it online.
You should be, yeah. I guess you said something about doing everything end to end. You want to learn the embedding model as part of this process, or?
Yes, I think it makes the most sense. But the close example would be the VJEPA model. But the VJEPA model does not learn a distribution of futures.
Mm-hmm.
And we kind of want the best of both worlds, right? So we want to learn an embedding online to discard irrelevant details, but the relevant details we do want to be generative. There we want to be able to predict different futures, and then yeah, for example, doing diffusion with let's say an online latent learning that is a bit complicated and has some challenges, but yeah.
So you think like something like DeltaToken is the next thing?
Yeah, that would be cool. Yeah. That would be cool. Yeah.
So it seems like there's kind of a couple different things you're talking about here. One is this like predicting the features from Dino V2 instead of predicting pixels, and the other is the sort of delta single token per frame representation. You talked some about comparisons against work that did the sort of Dino features without the delta. Are you aware of work that's, or have you tried to do the sort of delta representation, but directly predicting pixels instead of using the Dino features? And like, have you seen that, like, does that also converge? Does that sort of work at some level?
Yeah, it's a good question. I wanted to do it many times, but my co-author always said it was not interesting. So I haven't actually done it yet, but I think I will do it, because just to kind of prove my hypothesis there, that I think it must be much easier to do it in Dino space. Like, let's say doing diffusion in Dino latents is much easier. I would, it's maybe a bit different, but I would also say that doing this compression in Dino latents should be much easier. But in the end, if you have enough data and compute that.
Yeah, I guess the thing that surprises, like, you brought up the example at the beginning of like the self-driving car doesn't care about the positions of all the leaves, but like the positions of all the leaves are in the Dino features. Like
they are,
the Dino features has very high frequency information in it.
Yeah, so but the important, so I guess the important things become almost linearly separable, and the less important things now become are kind of harder to extract. But yeah, I thought it was very interesting that RAE can actually decode pixels from Dino features, like, it's surprisingly accurately. So always in my evaluations now, I just look at pixel videos again, and they're just decoded by RAE, and you're right, all this information is still in there, but it's kind of suppressed. And I think that by highlighting the important part makes it much easier for the world model is not going to focus as much anymore on the suppressed part, because there's like less incentive, like less, like it doesn't affect the loss as much as the very I don't have the right words, but I think you know
the
what
big
I mean.
stuff, the semantic stuff.
That's what contributes most of the loss. So that's the most thing that it will learn, and if it has capacity, it will also learn the smaller details. But except the things that are really like destroyed, like so Dino does kind of like, for example, text, like language on like written signs, they look weird. But now the new RE shows you can actually sum the latents, and you get that back too. So yeah.
Okay, thank you.
In the training data set, do you include data from autonomous vehicles or humanoid robotics?
Yeah, so for this paper in particular, I cannot disclose the training data set due to legal reasons. I wish I could, but we did release also a model on kinetics, which was trained after the submission. And kinetics does not contain robots. It does contain humans doing things, and it does not contain driving, like not contain like dash cam footage, but still it works on that on driving data sets, so seems to generalize. I've been doing some experiments on driving data sets now, but limited time.
I wonder if when we use cameras that are fixated with the pulse versus when the cameras are moving, whether the training results will see some differences.
The tokenizer or the world model, or both?
I guess I don't have an answer, but I'm just wondering.
Yeah, that's a good point. Definitely, like the camera movement is the first thing it kind of learns here, because it is the most, like, I guess you call it salient thing. Like, if you take that away, then it's definitely going to focus more on well, I guess in a self-driving data set you still have the car going forward, but it's not going all over the place. I don't have a much better answer to this question. Like, in the end, it's all movement and low dimensional enough to compress, and we can predict either, basically.
One more question.
Yeah.
You go ahead.
So I think this can work pretty well in a situation where the streams are kind of continuous, where the changes are like small. But what happens when the scene itself changes very drastically from one frame to the next?
Right. Yeah.
And you cannot fit in one token. Like error accumulation would be very high. Like how would you handle that?
Yes. So the trick I think there is to have a little bit higher frame rate in the beginning after the change, to allocate some more tokens basically to this new scene, if that makes sense. And then how exactly that's, I don't know if I can answer that technically right now, but I think that's like, I would say you could even, when there's a scene cut, you could even store all tokens again, right? As like a keyframe or something. That's also possible. Yeah, it really depends on the application if that is a problem or not. I mean, they're easy to detect, right? Scene cuts. There are different solutions to that problem.
But do you ever run into a situation where you know that the token has reached its limit and it cannot encode all of the information?
Oh yeah, you can just measure that, right? Because if you're doing the compression stage, then you can measure the loss, and if your loss is high, you can literally just take the first frame again and the reconstruction so far and improve your reconstruction. So do an iterative refinement basically of this frame until you think the reconstruction is good enough, and then you go to the next one. If that makes sense. So it becomes kind of like an RNN, where you spend some test time compute on getting enough information, but like you can get surprisingly good reconstruction even without considering the change. Just one frame from scratch. It's very easy to compress these latents. Yeah.
Thank you.
All right.
Any
Thank you,
other
everybody.
hot take questions? Hot questions, anybody?
I have one follow-up to this. So I guess that during test time though, how do you know, like, I guess like at what frame rate you want to predict? Because I guess you could have like some part of nothing happens, and then suddenly there's a lot of stuff happening in your video, right? And so I guess at that point you want to like sample much more tokens.
Yeah, so I can answer this for the context and for the generation. So for the context, it's easier because in the context we can measure it, right? And then for the generation part, that depends. If the world model wants to predict a lot of change, then we don't necessarily know that it wants to do that. So then we would have to come up with some way to have the world model decide its frame rate. Yeah, so that's.
Do you think that the DeltaToken could also, so you can like predict how many frames it's predicting into the future or something like that? Or?
Yeah, maybe you can not only predict the change, but also the temporal interval.
Right.
I'm sure that's possible.
Yeah, that makes sense. So but you want to kind of always predict the same amount of information for like prediction, I guess.
Well, it depends on the time stride, how much information it really is. So,
right.
I would say change the time stride, not the token per.
Yeah, that makes sense.
Yeah.
I like that. Yeah.
All right. Thank you.
Thank you.